Okay, so hello everyone, welcome. Can you hear me?
Yes, sir.
Okay, thank you. Okay, just we're waiting 1 minute for joining all of other participants, then we'll start this session. Okay, so hello everyone, welcome. So we'll start today's session. So basically today is our fourth number of class. Okay, so after completing the live 3 hours training program, then we talk about that problem solving class. Okay, so basically today's session I try to discuss about that how we can easily monitor the land surface temperature, as well as also how we can easily identify urban heat island, as well as also UTFVI index, how we can easily identify using Google Earth Engine and Landsat imagery. Okay, so let's go step by step. I will try to explain all of those things. So let me share my screen. Okay, can you see my screen?
Yes, sir.
Okay, so let's go. So today's session I try to discuss about that mainly how to remove cloud and haze from the satellite imagery, mainly Landsat or Sentinel imagery. From all those images, how we can remove the cloud and haze and get the neat and clean imagery. We also discuss about that. We also talk about that DEM data, digital elevation model, how we can easily visualize and also make the hillside map, slope map, aspect map, and other terrain profile, how we can easily create using the DEM data set. We also try to discuss about that. We also talk about the LST, mainly land surface temperature monitoring from Landsat satellite imagery. Previous class I discussed about the MODIS, how we can easily work for the MODIS and make the land surface temperature monitoring. Today's session I discuss about that how we can easily work with Landsat satellite imagery and make the land surface temperature mapping and also time series chart. We also talk about that how to calculate average, maximum, minimum pixel for any specific region. It can be NDVI, average, maximum, minimum, or LST, or urban heat island, maximum, minimum value, how we can easily calculate for any specific region. We also discuss about that. We also talk about the urban heat island and how we can easily make the urban heat island map. We also talk about that. And also how to monitor the urban thermal field variance index, UTFVI. Okay, and also talk about that how to make LST time series chart using Landsat imagery. Okay, so step by step I will try to explain all of those things, so I hope we can easily get the idea how it will work. So let's go. So let me open my screen. So LST, basically we already know about the MODIS satellite imagery we already use and make the LST map. But for a small area, we don't use the MODIS satellite imagery because this MODIS satellite image 1 pixel equal to 1000 meter. Okay, so very large pixel size. Okay, so for that, for the small study area, it also more better to use the Landsat imagery. So Landsat imagery we can get only for the 30 meter pixel area. So that's why we can easily make the more better LST map using Landsat imagery. So here you can see one kind of map, land surface temperature for Dhaka city year of 2020. And also you can see the urban heat island. We also discuss about that. From LST, how we can easily make the urban heat island. So basically urban heat island is one kind of phenomena. For this phenomena we find out that the high temperature nearby other region. Okay, so this time you can see it show about the high temperature, but other region, nearby region, it show about that normal temperature or low temperature. So there are a lot of region behind on the urban heat island. And we talk about that how to remove cloud from satellite imagery. So basically here you can see one kind of satellite imagery. Here we can find out this type of haze, also get this type of white color pixel. So basically it's the cloudy pixel. So when you apply the cloud marks band function, then we can get that all of cloud will be removed. We can get the very neat and clean imagery. And we also talk about that DEM data. So basically how we can easily use the DEM data and make the hill sheet map, slope map, aspect map. All of this I try to explain one by one. And how to calculate the average, maximum, minimum. So let's go try to practical all of those things one by one. So let me open my code editor. So just click on here and then find out your data set. Now we talk about that Landsat imagery. So just open your data catalog from you can get the Landsat. Just click on the Landsat. And here you can see about the Landsat 8 I want to use in here. Just click on here. And I want to use basically for the land use, land cover mapping or LST monitoring or urban heat island monitoring, we are using the surface reflectance imagery. Okay, so we can get that more better result when you want to use it for making the land surface temperature or land use, land cover mapping. So just I click on the surface reflectance dataset. So now it will go open all of full dataset. Here you can get about the Landsat 8 surface reflectance imagery. This imagery is available from year of 2013 to 2024 0730, and you can get about the all of band. Okay, so just I simply copy from here this image collection and then paste in my code editor. And further you can put any variable name. I put the name suppose image. Okay, so now this image collection we are just filtering. We already know about that how we can filter. First of all, where you need this image, for that we are using the filter bounds function, and then just simply import my study area. Suppose I want to make the LST map or urban heat island map for the region of interest of Dhaka city. Just I simply import the Dhaka city boundary shapefile from my asset tab. So if the default variable name as a table, I change the name. I put the name, suppose it's a RY, or you can put any name. So after that filter bounds, I just put the geometry. Geometry mainly it's our shapefile variable name, which is RY. and then you said that filter metadata. Suppose I want to choose all of less than 1% cloud cover image, so just put here that cloud cover, then less than 1. Okay, so then I want to make the map for year of 2020, so just simply filter your time period and mention about the 2020 1st January from year of 2020 December 31. So between this time I want to monitor the LST, as well also make the urban heat island map and also time series chart. Okay, so just simply put my time period, and then you can simply take the median. So then we take all of images median composite and further clip with our study area, which is RY. So now display this layer of your boundary shape file, and then I put here the image. So click to the run. It added the layer but not focus. For focusing, just use map.center object. Object is ROI and set here the 10. Click to the run. So now it visualize our study area. We can get this type of imagery. So now I want to set the visualization. Just click on here and then set the visualization. Suppose red, then green and blue band, and then custom stressing 98% for better looking, and further apply. And then also import this visualization parameter. Just copy this variable name and paste after the object name. So this is my object. After that, simply paste here, and then I put the name. It's a image. I just put the layer name. So now we can got our images. So this is our imagery. So now I want to use this image, and then further I want to make the LST or land surface temperature. Okay, then we further also make about the urban heat island and also make urban field thermal field variance index, UTFVI index. Okay, so if you search on the Google, then you can get that lot of algorithm. Suppose Landsat 8 for LST monitoring, then you can get lot of paper already published using this. So just I simply open. Okay, just I open this. So here you can see this is the one kind of algorithm they are using here to make the LST using the Landsat 8 satellite data. So basically here you can see they are used at the mainly 3 band. One band is the thermal infrared band, band 10, and another 2 band is the near infrared and red. So using the near infrared and red, they calculate NDVI, and further NDVI they are calculate about the vegetation proportion. Okay, and from the vegetation proportion they are calculate about the surface emissivity. Okay, and from the band 10 they are calculate about that brightness temperature. Okay, so using these things they also apply this manual window algorithm, and further they are make the LST. So in this time we try to apply this type of method, and then we try to make the LST. Okay, so this is our image. We already create this image, and this image have all of band. So you want to check how band name, just simply click on the print function and call this image, click to the run. So now it show you all of band. So basically this image have total 19 bands. Okay, so here in this time we are just use only for the 3 band. From this 19 band we just take only for the 3 band. One band is the near infrared band, another band is the red band, and another band is that brightness temperature or STB10. Okay, this band. So STB10, then band 4 and band 5, red, near infrared, and STB10. So these 3 band we need when you want to make the LST map. Okay, or monitor the land surface temperature monitoring. Just we need this type of map. Okay, so now first of all, our first step, we are just creating the NDVI. Okay, so just we already know how we can easily create the NDVI. Previous class I discussed about that. So first step, create the NDVI. So just take a variable. I put the variable name, suppose NDVI, and I call the image, and then use a normalized difference function between the two band, near infrared and red band. So just put here SR P5 and also put here that SR B4. Okay, so now it automatically calculated near minus red divided by near plus red. So further we are just display this layer of the NDVI, layer of NDVI, click to run. So now it display about that NDVI map. We can get the result as a grayscale. If you want, you can also add the color. Suppose I just add the mean -1, then max +1, and put the plated, and I put the color such as blue, then suppose white, and for vegetation green. It will run. So now it also set the color. Okay. So now we can get this NDVI map look like that. So this is our first step. To make the LST, we have to create the NDVI map. Okay, and in this time I also, you can see here, when I click on the inspector tab and click on this map, then I can get the value for a specific coordinate. What is the NDVI value? We can easily get it. So here you can see it show about that 0.2, mainly ND, because I don't put any rename. So just I put here the rename function, then we can get, I rename it as a NDVI. If you run. So now when I click on this map, it show about that NDVI result. Suppose I just click on this map. Click on this map. So now it show the result for NDVI. So here you can see it show about that NDVI. Okay, because I rename it as a NDVI. Okay, so after creating the NDVI, we are talk about that vegetation proportion. You can see about the vegetation proportion. It also called about that fractional vegetation. You can easily get the more information from this paper. Just I simply open this paper. Okay, just I open this full paper. Okay, so here you can see about that land surface. So here you can see about that proportion vegetation. So let me increase the file size. Okay. So here you can see this is the formula about that. This is the proportion vegetation, represent the vegetation proportion, and also can about see the citation about that. So this is the formula about that. This formula is that NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value, and then power 2. Okay, so this is our formula. This is formula called that proportion vegetation or fractional vegetation. Okay, so now we are use this equation and then calculate the proportion vegetation or fractional vegetation. So in this formula here you can see, first of all we need to calculate about the NDVI minimum value and also NDVI maximum value we need to calculate. So here you can see we already make the NDVI map. So now from this map we are just take the information for NDVI mean value and NDVI maximum value. Then we can easily apply it. So for doing this thing, just I take a variable. Suppose I put the variable name is that mean equal. I just call the NDVI. This is this variable stored this map. So now from this map, I want to extract the minimum value of NDVI. Okay. So just use a function dot reduce region. We already know about the reduce region function. Basically, this function help you to get the band's statistical value for a specific boundary. Suppose for this Dhaka city boundary, I want to calculate what's the minimum NDVI value. So then I simply use the reduce region function and further just put all of argument one by one. Then we can easily compute the minimum NDVI value. So just I simply make a dictionary. So curly bracket start and also curly bracket int. And then reducer. So in this time I want to calculate the minimum value. So that's why reducer will be e dot reducer dot min. Geometry, it's your boundary shape file which is RY. Scale is the resolution of your satellite images, 30 meter. Then it's not need, I remove that. It's not need, remove that. So now I just print that. Suppose print that mean and click to the run. So now it's computing the minimum value of NDVI in Dhaka city. We can get the result from the console tab. Just click on the object. So here you can see you can get that this is the value for minimum NDVI in Dhaka city year of 2020. Okay. Now you can see we can get the result as a dictionary. This result have a keyword and also key value. So it's a dictionary. Keyword and key value make a one item, and we already know about that. It's called the dictionary. This is the keyword and this is the key value. But in this time we are just need only for this value. Okay, we are not need the keyword. This keyword we don't need. We are just need only for this value. So for that we are just use a code. Basically we are just write the code in here. Just use at the values. Then we can get only for the value, only for this number, and then use at the get function, and these values I get from the first item. And JavaScript is a zero base, so just we are put here the zero. Zero refers to the first item of this dictionary. Okay, so just you can see I just need only for this value. So further I simply use at the values, and these values come from the first item. And JavaScript programming, first item refers to the zero. So just I put here the zero. So now I run the code again. So now it computing only for this value without dictionary. We can get only for this value. Okay, NDVI minimum value we can easily get it. But this value you can see here. I just click on here. It show about that computed object. Okay, computed object. But this value I want to use as a number. I need this value as a number because this is my equation. NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value. So I need the number. I don't need for the computed object. I just need the number. It's about the computed object. So now I convert into number. It's very easy. Just you can simply use a function e dot number. Okay. So now we define the number and we can compute. We can get only for this value as a number. So now you can see when I run the code, it shows about that number computing. Okay. So now we can get the number. Minimum value of NDVI we can got as a number. So further, this number we can easily use it for our main equation. Basically this equation we can easily input in here, and then we can easily calculate the proportion vegetation. Okay, now we are doing for the same for maximum NDVI. Just I simply copy the same code. and then paste here. I change the variable name, suppose max, and also put here that max. And now I print that max. Click to the run. So now it's computing the maximum NDVI value 0.4. Okay. So now we can easily apply the proportion vegetation. It also called the fractional vegetation. We can easily calculate. Okay. So just we are applying this formula, NDVI minus NDVI mean value divided by NDVI maximum value minus NDVI mean value. Then we can easily get the result of proportion vegetation or fractional vegetation. So now let's go try to do it. So for doing this thing, just take a variable. I put the variable and suppose FV or fractional vegetation. You can put any variable. I just call the NDVI. This NDVI subtract with NDVI mean value. Okay. This variable stored the NDVI mean value. I simply copy and paste here. And then divided by max value subtract with mean value. Okay, so this is as well as also we have power 2. Okay, and this full equation just I simply close and also start in here. So now I just this full equation just I put the power 2. Okay, just use here the POW power and then put here that 2. So this is a 2 is a number, so that's why I put here EE dot number and then input the 2. So it's a power 2. And further I just put here the dot rename function, dot rename as a FV. Okay, so now display this fractional vegetation. Just put here map dot add layer and call the FV. Click to the run. Get another layer of fractional vegetation or proportion vegetation. If you want, you can also add the color. Suppose I just simply add the color from here. Just click on here, and then it's tracing suppose 98%, and then add the color. I just add the color. Suppose blue, then suppose white, and then put here the suppose green, and then apply. And also import copy this visualization parameter and apply after the object name, and I put the layer name. It's a fractional vegetation. So now we can get the another layer, fractional vegetation. So now we calculate about that another parameter, surface emissivity. Okay, these things we calculate. So they already provide a equation. So we try to apply this equation in here. So here you can see this is the formula about that land surface emissivity. So here we find out some constant value such as you can see 0.9680. Okay, then also you can see about that 0.860 multiple the fractional vegetation. So just we try to apply this type of formula and then we try to calculate this surface emissivity. Okay, so let's go. For this, just I take a variable. Suppose I put the variable name is the A, and then I put here EE dot number and stored this value. Suppose 0.004. It's a constant value. We can get the constant value from the equation. Take the another variable, suppose B, and EE dot number 0.986. So it also come from this equation. And now we can just take a variable, suppose EM equal FV fractional vegetation, it's multiply with 0.004, which is including in the A variable. I simply copy the A and paste here, and then add with B, mainly 0.986. I simply copy and paste here. So this is the formula about that surface emissivity, and further I put the rename it. Suppose I put the name rename as a EMM, or you can put any name, and then further I display this result map.add layer EM. Click on. So now we can get the another layer of surface emissivity. Okay, it look like that. Just I simply click on here and add the visualization of surface emissivity, and then apply. Okay, so if you want, you can also add the color. Suppose I add the color of surface emissivity. Suppose blue, where is the low? Then suppose look at that green. Look at that yellow, and high show as a red color for surface emissivity value. Just apply. So we can get this type of map. I just simply import and further copy this variable name of visualization parameter. Simply copy and paste after the object name, and I put the layer name, suppose EMM or surface emissivity. I just put in here. So now it will be set with our code. Okay, so now we can get another layer of surface emissivity, and further in this time we talk about the another band. Mainly this band is that brightness temperature. Okay, so STB10. Okay, we try to calculate these things. So in the STB10 we can easily get this band from our satellite imagery. So here you can see this is the imagery. It already provide this band STB10. Basically it's the band 10 surface temperature, and we can get the surface temperature unit is the Kelvin unit. We can get the result, and here you can see about that this is the scale value and this is the offset value, okay, of this band. Okay, so in this time this value we also need to get the proper pixel of LST result. Okay, without if I not rescaling the scale, then we don't get the proper pixel of LST value. So that's why it's very important. We need to reproject this scale value of STB10 bands, and further we have just used this type of information. So let's go try to do it. So just take a variable. I put the variable name, suppose thermal, and then I call the image. From this image I just select the specific band, mainly STB10. So this is our band name. So this band we are just simply rescaling. For rescaling, just multiply with scale value. So this is the scale value. Here you can see this is the scale value. This scale value we multiply and further add with offset value. So this is the value for offset of this band STB10. Copy and paste here. Okay. So now it rescaling. And further, if you want, you can simply display this result of thermal band. So I will just put here map dot cat layer and call the thermal. Click to run. So now it added another layer of thermal. It look like this. Just I simply click on here. And then stressing, then apply. So now you can get that this type of result. This type of white color have a high reflectance of the thermal bands. We can get it. So I just use the gray color. Just I import and then copy this visualization parameter variable name and paste after the object name of the last layer. So just paste here and I put the layer name. It's a thermal band. Okay. So now we are applying. We can get all of necessary band, such as first of all we simply import our images. So this is our satellite images. From this satellite images we extract the information of NDVI. From the NDVI we calculate about the fractional NDVI. Then we calculate about the surface emissivity, and then we calculate about the thermal band. Okay. So now we can get all of layer, all of things we can easily get it. So now we can apply the final algorithm. Mainly we calculate the LST using the equation. So just I write the code, then I explain. Suppose I just take a variable of LST.
Can you hear me?
And then I just call this thermal band and use here the expression. Okay, just I put my equation to calculate the LST. So in this equation, we are just write the equation first of all. Just write the equation. This equation is that TB divided by 1 plus 0.00115. It's multiply with TB divided by 1.438. Okay, then after doing these things, it also multiply with logarithm surface emissivity. Mainly I put the, suppose it's EP. Okay, and this result mainly we can get as a Kelvin. When I subtract this value, suppose I subtract 273.15, then we can got the result in degree Celsius. Okay, when I subtract this value. So now this expression here you can see TB and EP. So this is our two variable. So we already know about that, how we can easily work with expression. So after writing your equation, just put the comma sign and then put the curly bracket. In this curly bracket, I define what is the TB. Okay, TB mainly it's come from the thermal band. So just I put here the thermal and select the STB10. Okay, it's our thermal band. And EP means surface emissivity. So just I mentioned about that EP, and it's come from this EM, and then select the band name EMM. So here you can say I already, when I just, you can say I put the EM layer name and I rename it EMM. So just same things we are also writing here. EP basically it is the surface emissivity. Select the EMM band. Okay, and further I just rename it as a LST. So now further we display this result. Suppose just map dot add layer and call the LST, click the run. So now it visualize our final map of land surface temperature as a grayscale.
Hello.
Yeah, please.
You can see that. I can see that for the LST.
Yeah, just a minute. Hold on. Yes, please. Now.
See that for the finding the term, use the scaling process multiply by it. Why is it that when we're finding the NDVI bits, when we use the font, we didn't multiply the scaling factor? It's on the
Which one?
For your terminal, if you look at your terminal, where you calculate your terminal, you image the select and then multiply by the scaling factor.
This one.
No, the one above it.
This one.
Yeah. Yes. So it's image dot select and the bound and you multiply with the scaling factor. Right? Yes.
Yeah. Okay. So now, it's multiply for the represented the pixel of STB10. Okay. So this type of STB10 basically we calculate the LST from thermal band. Okay, in this time depend on the thermal band we calculate the land surface temperature, and that's the region. If I ignore this type of rescaling, basically in this time we already know about the rescaling for Moody's NDVI or other things, but this time this new data set, already you can see this data set have some scale value and also their offset value. So when you can get the scale and offset for any data set, not only for that, this scale value multiply and offset will be add. So you can see about their common example about that. You can see they also multiply the scale value and add with the offset value. Okay, for rescaling.
Yeah, we didn't do that with the bound selected NDVI.
Okay, but for the other band we are not considering because in this time our main factor is thermal. Okay, because our LST depend on the thermal band. But if you also rescaling the other band, it also there is no problem. Okay, but suppose you can see here when I write the NDVI or other, we are not rescaling this type of band. But if you want, you can also rescaling, then it also not a problem. But if I ignore this part, suppose I don't rescaling this thermal band, then it create the problem. We don't get the proper LST value. Okay, so but if we, yeah.
Okay, thank you.
Yeah. So that's why we are just it's compulsory need. So that's why I just multiply, but it's optional. If you want, you can also add the scale and offset value for other band SRB5 or SRB4. It also okay. There is no problem. But it also better. It must be we need to use on the thermal band because in this equation here you can see mainly this equation depend on the thermal band. Okay, so that's why we are just rescaling the thermal band and then we can get the LST. So now we are just trying to show the map. It look this type of color. So just try to add in here proper map. Just stressing suppose 98%. So you can see 22 degrees Celsius to 35. So it's maintained the range. So just I try to add the visualization for click on the plated and then I set some color. Suppose low LST value show as a blue color and greater than blue color I want to show this type of yellow color. Greater than yellow I want to show suppose show green, then we put the yellow color, then put at the high temperature show as a red color. Just I put this type of sequence of color. Okay, so now try to apply So now we can get this type of result for LST. Here we find out that this type of region identify about the high temperature. Okay, or if you want to check the other, suppose click on the stressing 3 sigma and then apply, then check which is looking more better, just try to use it. Okay, suppose you can see in this time when I put here this stressing, then I can get this type of mapping. Okay, so this stressing is one kind of visualization process. Using the stresses we can get the data set for the different range we can apply, and then we can easily stress the data, and we can it also very visualize. So here you can see when I change the different types of stressing, this range is also changed. Okay, so which one is more better for you, just simply use it. Suppose in this time I just use it. Okay, so this type of rate can identify about the high temperature, mainly 31 degrees Celsius or more than 31 degrees Celsius, identify about this type of red color. You can also check it from here. Just I simply import, and further just click on the inspector tab, and then I simply click on here. So now it shows about that the temperature. We can get this 35.1 degrees Celsius. Okay, so this type of red color identify about that. You can see when I stressing, it also show about the value 31. So this type of red color identify about that 31 or more than 31 temperature. This type of red color have. Okay, so this type of blue color identify about that 24 or lower than 24. Suppose I click on this water body, so we can check the result from here. Here we can get the result 22. Okay, so lower than 24 or 24 or lower than 24, we can get this type of blue color. So this is the map of LST. Further, this LST map we are use and then make the urban heat island map. Okay, so how I can easily make the urban heat island map? So basically urban heat island map have a formula. We are just use this formula, and then we can easily calculate for urban heat island and also make the urban heat island map, as well as also make the time series chart of urban heat island or LST. Let's go try to discuss about that urban heat island. So okay, we also need to add with the visualization. Just I simply copy, then it will be set with our map and paste after the object name. Just paste here and then put here that it's a LST. Okay, so this is our LST map, we can get it. So now from this LST we have to calculate urban heat island. Okay, so this formula is that, okay, let me write the formula for urban heat island. USI equal, this formula is that LST minus average LST divided by standard deviation LST. Okay, so this is the formula, okay, for that urban heat island. So LST, we already make the LST map. So now from this LST we subtract with average LST and divided by standard deviation of LST. Okay, so now according to this formula we need the two new values. One value for LST average. From this map we have to calculate the average value of LST, as well as we also need to calculate about the standard deviation value of LST from this map. So let's go try to calculate the average LST. Just take a variable, suppose average LST, and I call the LST. We already know about that. We have to use the reduce region, and we input all of things one by one. So just make a curly bracket start and also curly bracket int. Okay, and then I put all of things one by one. So first of all, reducer, I want to calculate the average. So just put here ee dot reducer dot mean, and then geometry, it's our shapefile variable name. So basically RY. Scale is that 30 meter. So now remove all of those things, it's not needed this time. Okay, so now we are just printing the result of average LST and then click to the run. So now it's computing this value as a dictionary. We can get the keyword and key value about that average LST, but I just need only for these values. For that we are just use the same function values and get from first item, and I just need only for the number. So just put here ee dot number, so then we can compute only get only for the number. So click the run. So now we can get only for the average LST value for my study area. I also need the standard deviation value. So just I simply copy the same code and use it, paste here. So just I change the variable name. Suppose it's a std lst, and then I also change it in here the function std dev, standard deviation. Just copy this variable name and then print it. So click to run. So now it also computed the standard deviation value of LST. Okay, we can get 1.9.8 degrees Celsius. So after getting this value, I apply this formula. Okay, so for this formula it's very easy. Just take a variable, suppose urban heat island, and then we are just calculate this equation. So LST, it subtract with your average result. I simply copy the average LST. Further, these things also divide with your standard deviation of LST. Simply copy and paste there. So now we are just add a layer, map.add layer of USI, click run. So now it shows about that urban heat island map we can generate from here. Okay, so now we can get this type of grayscale color. So here you can see this type of white color. It's indicating about that high temperature region. Okay, then nearby there are low temperature. This type of red color identify about the low temperature. So urban heat island are urbanized areas that experience higher temperature than outlying layers, such as you can see the in this time building or barren land or other infrastructure absorb the lot of sun's heat. So that's why we can get the high temperature near the other region. Suppose it's a vegetation or other things. So that's why we can get it also more better. Suppose I just try to add here that color. Suppose just I add here the color. Suppose I want to suppose blue color for normal temperature, then green color, then yellow color, then put here that red color for high temperature. Further apply. So now I can get this type of map. Here you can see. So basically this type of red zone identify about that urban heat island. So just I simply increase this map. So here you can see this type of region, we find out that high temperature. So urban areas usually experience that urban heat island, the effect, and basically there are significant warmer. So this type of significant warmer than surrounding areas. So this type of is the low temperature. For this, basically this is the full cities. So that's why you can get this type of, it's a full urban area. Okay, so that's why you can get this type of result. So basically for this we can find out this type of red color. It's about the warmer than this type of region. Okay, this type of region, but it's not much more, almost same, but this type of red color I did significant more warmer than this type of blue color region. Okay, so this type of red color is the more warmer than this type of blue color region. So this is our urban heat island. We can easily find out from here for this Dhaka city region. And if you want, you can also change the stressing level. Suppose I put the 98% and then further apply. So now we can get that. You can see now you can get this type of map, or also change the other stressing level. So for that we can get the different types of visualization when I use at this type of stressing level. Okay, or is the normal is also okay, or when you export this map, then we can easily get that proper value. When you import this map in ArcMap software, then you can get that proper value, then you can easily make the map about the urban heat island. So this is our urban heat island map. So now if you want, you can also make the time series chart. Suppose I want to make the time series chart of LST, or land surface temperature, as well as we also make the time series chart for urban heat island, as well as we also talk about the another topic, mainly it's that urban thermal field variance index. If you want, you can also calculate same things, just put the formula, then you can easily get it, UTFVI index. So now we try to discuss about the time series chart, how we can easily make this time series chart. We discuss about that. Suppose we already make the LST map. So this is our LST map. So now I want to make the time series chart of LST using the Landsat satellite imagery. So in this time, you can see there is no band about that LST. Okay, so previous class I discussed about that, how we can easily create the band, we already discussed. So now we also trying applying the same things also in here, and then we are just make the LST band. Okay, and then make the time series chart of LST. Okay, so now discuss about that time series chart of LST. So LST. Okay, so before that, anyone any question you can ask me for this code, full code. Anyone any question or any confusion, you can ask me. Okay, scale is mainly Landsat image scale is that 30 meter resolution. So that's why you will also use at the 30. Okay, because 30 meter is that Landsat imagery resolution. Okay, so for that we are just print. Suppose in this time when I make the LST time series chart, we must need the number of image collection. Okay, so because when you want to make the time series chart, you must need the collection, image collection. Without image collection, we cannot create the time series chart. So in this time I will show you that how we can easily get that image collection, and further we try to use the image collection and make the land surface LST time series chart. Okay, and stressing basically it's one kind of your visualization process for data. So when I change the stressing level, it automatically changes the mean and max value from my map and display the result. Okay, so this is the process about that. So here when you can see when I use that, sometime I use at the 80%, 90%. So basically which stressing look more better for your map, you can just use it, then you can easily get that more better map. Okay,